My name is Eric Brandwein, and I'm with the AWS security team. But back when I joined Amazon, I was with a team that defined and launched VPC, and that's what we're going to be talking about today. I first gave a version of this talk a few years ago at reInvent. I gave it again at reInvent last year. So there's some new content, but it's largely a reprise of the previous talk. I would rather you leave angry and disappointed early in the talk than angry and disappointed at the end of the talk. So this is your caveat. The problem that we're trying to solve here is that we've got the cloud, and we're AWS. We like the cloud. And the cloud is full of all sorts of goodness. We started off with EC2. It's compute. You can get various sized instances from us. But there's all sorts of other things that you can get in the cloud, all sorts of compute and networking primitives that you can connect to it. Things like elastic load balancing, the elastic block store, relational database service, Amazon Redshift, Elasticache. We keep launching new services. We keep adding things to the cloud. But customers have data centers. And these are perfectly good data centers. They're expensive data centers. They're data centers that customers don't want to abandon. There's all sorts of hardware in there that's still useful, and they want to take advantage of it. There's going to be no big bang migration. And so, like all good engineers, we go to the whiteboard, and you, or perhaps more likely your boss, is just going to draw an arrow on the whiteboard and say, we need to connect the data center to the cloud. How hard could this possibly be? This is going to be an insanely important deployment scenario for us. This morning, Matt talked about the journey to the cloud. And even as we have customers that are going all in and turning off their existing data centers, we've got another customer that's just starting out on this journey. And so we're always going to have customers that are at some point in the journey where they're going to need to connect their existing resources in their on-premise data centers to their resources in the cloud. And our poster child here is Amazon. We had data centers before we had the cloud. And they were pretty remarkable data centers. It was from our own data centers that the idea for AWS grew, but they're still not AWS. And we had to move our applications, starting with, among other things, the retail website, which hopefully all of you are familiar with, into the cloud. And this could not be a big bang migration. There was no magical forklift that would drive and pick the website up and drop it off into the cloud. We had to move incrementally, just as all of our customers do. And VPC played a critical role in that migration. Laura Gritt did a talk on this at the first reInvent entitled Drinking Your Own Champagne. It's available on YouTube if anyone's interested. So the whiteboard engineering is easy. You draw the arrow and you're done. But in the real world, there's technical challenges. And EC2, as we originally launched it, you would launch an instance and it would have an IP address. And this IP address was effectively a 32-bit random number. It was your 32-bit random number. We guaranteed that no other instance had this 32-bit random number, but it wasn't meaningful. They weren't grouped together. If you launched another instance, it would get a different 32-bit random number. And complete strangers could launch right next to you. Another customer could launch an instance, and you can see 12.4 and 12.5 are adjacent IP addresses. And the fact that those two IP addresses are close together doesn't mean that they're owned by the same people, that they're performing the same task, that they're related to each other in any way, shape, or form. And so as this would go on with customers launching and terminating instances, they would get these IP addresses that were effectively randomly assigned. And so when you draw that arrow on the whiteboard and you attempt to connect your data center to the cloud, you run into problems. This customer has chosen to number their data center out of 192.168/16. This is neither a good choice nor a bad choice. It's just a choice. It's a CIDR block. They picked it. They probably built this data center before AWS even existed. They weren't thinking about cloud migration. Heck, if the network engineer that designed this had started talking about cloud migration, they would have fired him and gotten someone that could build a data center. So this is a number. They're going to have a router. This is going to be a sheet metal appliance. It's going to be blue or green or some other color. And it's going to have a routing table. And the routing table is going to say 192.168.00/16 stays here. This is mine. It stays here. So as we launch instances, we need to tell this router, 10.44.12.4, that goes to AWS. And as new destinations show up in AWS, we have to add them to the routing table. But remember, the IP address right next door might not be yours. So we're forced to add /32 host routes. We can't add a larger aggregate. So every time this orange customer launches an instance, we have to add something to their routing table. Every time they terminate an instance, we have to make sure we pull that route from their routing table, because that IP address could be reassigned to another customer later. So we've now made it such that the routing table at the customer data center, one, is as large as the number of instances that they've launched. We have customers that are running tens of thousands of instances. This is a good way to break routers. And two, the routing table changes with the velocity of instance launch and terminate, which is an even better way to break routers. But that's not all. What if, back in the dawn of time, the network engineer had picked 10.44/16? This is neither a good nor a bad choice. The cloud didn't exist. They weren't thinking about moving to AWS. There is absolutely nothing that you can put in that routing table that will teach that router that some of 10.44 lives here and some of 10.44 lives there. If you've got a 10.44.12.4 here and a 10.44.12.4 there, you're done. That IP address is no longer unique within your namespace, and you can't reliably route to it. Now, someone out there in the audience is thinking double NAT. Double NAT does technically solve the problem. I once mentioned double NAT back at the office. It turns out network engineers have a stash of torches and pitchforks in their offices for just such cases. So double NAT's a bad thing. We need to figure out how to resolve this routing conflict. And customers have already built their data centers. They've already laid out their IP space. There is no block of addresses that a priori we know is not going to be in conflict with any customer. So in order to do this, in order to actually pull this off in the real world, not just the whiteboard, we need customer-selected IP addresses. Customers got to be able to bring their own IP range. For whatever reasons they want to use it, it's their IP range and it's perfectly valid. And we need to stop breaking routers. We can't have routing table updates being driven with instance launch and terminate. It has to be on the gross network change scale. And we need to conform with existing network designs. People have already designed networks. And again, they aren't good or bad, they're what they have. A lot of our customers have design standards, security standards, compliance standards. In order to build an application in company.com, you have to do these things. And I don't want to have the conversation with every customer about how you rebuild your infrastructure so you can adopt AWS. I want you to be able to bring your existing infrastructure and to use as much of it as possible in the cloud, and then iterate on it as you need to change things. So as an example, we had one early beta customer, and this customer's host provisioning tools, host management tools, assumed that all networks were /24. And they told us, there's no way we can use this product unless you support /24 networks. Now, the cool thing is that that was one API call by them. They just defined /24 subnets. They actually didn't even need to talk to us about it. And honestly, Scout's honor, that customer was Amazon. We had this amazing programmatic infrastructure, but it was all bespoke. No one that built that infrastructure had ever assumed it would run outside of our data centers. And all of the networks, each rack was its own /24. There was never anything that wasn't a /24. The tools didn't account for it. And so they had these fragile tools. They were really robust in the face of their normal workload, but they were fragile when you took them outside of their environment. Fine, we'll make /24 networks in the cloud. The host provisioning tools work just fine. So that leads us to the presentation, the product definition that we want to give to customers. You've got a data center on-premise. You create a VPC. Part of creating a VPC, you supply us with a CIDR block. You can pick any CIDR block you want, literally. I don't care what it is, routable IP space you own, IP space you don't own, RFC 1918, you give us a CIDR block. We administratively limit you to a /16 in the APIs, but during testing, we actually created /0 VPCs. It's hard to talk to them, you can't get packets in or out, but it's completely functional. You create a VPN gateway. This is our end of a private connection with your data center. Then you declare a customer gateway. There is no API for creating a router on your premise, but there is an API for telling us about a router that already exists. And then you bring up a VPN connection between the two. And when your router learns about the new route, you get one new route for that VPC. So we've added one route to your router's route table. This is a good way to not break routers. This is something that routers are good at. And that route comes and goes as that VPN tunnel comes and goes, which is relatively infrequently. You can now lay out subnets inside of your VPC. Again, this is all API driven. And then you can launch and terminate instances to your heart's content, and only the aggregate for the VPC appears in your route table, and your router doesn't need to know about the velocity of instance launch and terminate. So you're saying, I stuck around for this. Like, you're going to tell me about virtual networking. This has existed for decades. I've been able to buy this. It's built into the Linux kernel. Like, what are you talking about? The thing that you're calling a subnet is just a VLAN. The thing that you're calling a VPC, there's a router in the middle of it to connect all of these subnets together. That's just a VRF, virtual routing and forwarding. But the design that we're talking about has that same presentation, but the requirements for it, the implementation requirements for it are very different. If we were to do this using traditional networking primitives, we would be operating far outside the common envelope. So VLAN space, 12 bits, 4096. And you know someone was writing the RFC, and this is one of those hard-fought things. Like 12 is a weird number. You know, they were arguing over which bits went where and whether they needed to make it 8,000 or they could get away with 2,000. But in reality, if you look at a typical data center, like, are you really going to carve an L2 domain up into more than 4,000 chunks? Like, 12 bits is perfectly reasonable for traditional networking. But I was watching an Andy Jassy presentation recently, and we publicly claim over 1 million customers. 1 million is larger than 4,000. VRF support. There are routers that claim multiple thousands of VRFs, but you talk to the vendors, you talk to the customers that have adopted these features, and none of them are using it at anywhere near that scale. They're using tens, low hundreds. They're not using thousands of them. And there's a name for people that are the first to use a feature like that in production. You're called a beta tester. And that was not the position we wanted to be in when we were building this product. But that's not all. Even by the numbers, just looking at this, we think it's tough. But there's a fixed ratio of VLANs to VRFs. And we'll see how that's a problem in a moment. We talk about these big routers. And they're physically big. Like, they're impressive devices. It's a whole rack. Some of them are multi-rack. The power delivered to some of these routers is measured in tens of kilowatts. These are literally blast furnace devices. Like, if you stood behind them, you could cook. But what we're talking about there is really the data plane. This is the esoteric memory and the custom ASICs and the high bandwidth fabric cards. This is where you talk about terabits. This is where you talk about all of the big impressive numbers. And buried in that big router is a little tiny control plane. It has less power than this laptop. It has less memory than this laptop. On the plus side, it's the most expensive memory I've ever bought, but it has less power than the machine that I'm using to drive PowerPoint today. And that's what's actually the brain of the router. And it's connected to the data plane via what's effectively a tiny little straw. And the way you get availability with these things is you buy another one, and you bring up 1 + 1 failover. But it's the control planes that are talking to each other. And you know that millions of times, someone has tripped over a power cord, knocked one of these things out, and the BGP session between them reconverges. This happens all the time. That code path is well trod. It works. We know it works. It's happening constantly. Bring up 1,000 MP BGP sessions between those two control planes. We actually were able, in one router model, to cause it to bury the CPU so hard that it would miss a watchdog, and the surviving device would reload. And so the first device would come up and attempt to establish 1,000 MP BGP sessions, miss a watchdog, and reload. So you had this bouncing router pair, and it would actually never reconverge to anything that would pass packets. We had to intervene, bump the configs. This is not the position you want to be in. Another way that we were stressing these things out, routers are configured using text files, ordinary plain Jane text files. If you assume that a router configuration is about 50 characters, it takes about 10 lines to configure a VPC, set up the VRF, all of the BGP stuff that you need. Customers use on average 4 subnets per VPC. It takes about 5 lines to configure a subnet. The total config, and we have about 2,000 customers. It's reasonable, about 2K VRFs. It's a 3 megabyte text file. In reality, when we were testing this in the lab, we were pushing config files of about 5 megabytes. It took one of these devices 5 minutes to parse the config. So you'd hit return, and for 5 minutes, the control plane would do nothing while it was parsing the configuration. And it's not that these are bad devices. It's that we are operating them far outside of their intended envelope. This is a design that the designer of the router never considered. It wasn't even in their thoughts when they built this thing, which is fine. It's a perfectly good device. But routers are built by human beings. They're just strange computers with expensive hardware on them. And they have the same sets of bugs and the same sets of implicit assumptions that go into all of the software that we all write. We had another device where they used linked lists to manage certain internal structures. Typical users of this feature had between 5 and 10 of these things. Chasing a linked list that's 10 items long is noise. It's a couple of clock cycles. It's a few memory accesses. You don't even notice it. We've had router configs that had thousands of these things. And so as the config gets longer, parsing the config takes longer, and chasing down that linked list gets longer, and the router falls over. We had another router, and this bug was present since the very early versions of this router vendor's firmware, and no one had ever run into it. It turns out that when you committed the config on this router, it would leak 4 words of memory. How often does a router have its config committed? You configure it, what, half a dozen times when the router is new. You get it as a good upstanding member of the network. Heck, it'll probably reload before you have to configure it again. We're driving config at these devices at the rate at which our customers are making API calls. And plus you're doing 1 + 1 failover, but you have to have 2 routers so that you can configure the customer with high availability. You want the customer's objects to be configured on 2 routers. So we're driving config to 2 devices in lockstep, leaking memory, and they both ran out of memory at almost exactly the same time, so we had a correlated failure. This is a mature router vendor. They'd been in the market for years, and this bug had existed in the market for years because no one ran into it. We were outside of the common envelope. This is not the way to build a service. So by the numbers, the protocols don't work. If a VLAN is a subnet, that means that everywhere that a customer has instances within a subnet, I have to stretch that VLAN. And as VLANs get larger and larger, pitchforks and torches start appearing. We like owning our own destiny. As the examples that I've just gone through show, we run into strange corner cases, unusual bugs in these devices. They're not the things that a lot of customers of these router vendors are going to run into, and we want to be able to fix them on our own timescales. They're very important to us. They're not important to the aggregate of that router vendor's customer base. And we want to be able to change our minds. We want to be able to move from vendor to vendor depending on pricing and availability and local support and things like that. And when you get into these advanced features, interoperability is poor. But that's not all. We all talk about horizontal scaling. Amazon is very familiar with horizontal scaling. And this looks like horizontal scaling, but it's not horizontal scaling. It's silos of capacity. So I stopped at 4 VPCs per router pair and 40 instances per router pair because I didn't want to draw all the little boxes in PowerPoint. But it's a realistic example. The customer shows up. I've got these 2 silos available, and I arbitrarily choose the left one. So I place customer A in the left silo. I've consumed 3 instances worth of capacity, 1 VPC's worth of capacity. Customer B shows up, I place them on the right. I've got some sort of load balancing algorithm. It could be as simple as complicated as we want. Customer C shows up, I round robin back to the left. Customer D, I place them on the right. Life is good so far. Customer A launches 2 more instances. Their VPC is in the left router pair. I must place their new instances in the left router pair. Otherwise, they're not in that VPC. Customer E, I choose to place them on the left as well. It's only 1 instance. This is a very important customer. This is the getting started instance. This is a customer that just signed up with a credit card. Every single one of our customers was once a 1 instance customer. Everyone got started really small. And we don't know if this customer E is going to be the next Netflix or Philips. They may also just stay a 1 instance customer forever. Customer F, this was a large enterprise customer that moved over. This was a predicted move. We forecasted this capacity. That was easy. And then customer G. This router is full. I'm out of VPC capacity. I can sell the remaining instance capacity to any of the customers that are on that left router pair, but I can't sell it to anyone else. And I can hide this if I have to behind higher prices. I'm going to have to maintain a slush fund. I'm going to have to maintain a buffer And so I'm going to drive down the utilization of my instance capacity, but I can hide this from customers. Now, customer B, this is a social media app that went viral. They're having the best day of their lives. They've exhausted instance capacity on that router pair. And we're out. There's no more instance capacity for them. If they want one more instance, we're going to have to do something unnatural. They're going to have to create another VPC. There's going to be some break in the customer experience. And this I can't hide. This is something that customers will run into. And we see customer fluctuations in the thousands of instances on a regular basis. That's a huge slush fund to have to maintain on a per silo basis. So that leads us to the implementation requirements, the things that we have to have in the actual implementation. And this was a literal statement from our design documents. We needed to be able to support millions of environments the size of Amazon.com. So there's a little bit of think big in there. And we must not further constrain the placement problem. Placement is a miserable problem. When you add in things like placement groups, you want all of your instances linked together with a tight high bandwidth network and different instance types and the location of your EBS volumes. There are enough constraints on the placement problem as it is. The network must add no new constraints. So that leads us to the implementation that we actually fielded. We have servers. Someone has to own the sheet metal. In the case of AWS, that's us. And they have IP addresses. It's no secret. We run a physical network with IP addresses on it. On those physical servers, we place instances. The instances also get IP addresses, but they're pulled from the customer's VPC range. These instances are grouped together into VPCs. And I am using color to indicate VPC ID. So we've got 3 different VPCs running around here. And then there's one more component that's not exposed to customers, but it's the linchpin around which all of VPC revolves, and that's the mapping service. Let's do a quick Ethernet refresher. We've got 2 hosts. They're connected back-to-back across an Ethernet switch. Everything is freshly booted and working correctly. 10.0.0.2 is going to ARP for 10.0.0.3. The Ethernet switch is going to have no idea where anything is because it's freshly booted, so it's going to flood that ARP request out all ports, including the port to which 10.0.0.3 is connected. 10.0.0.3 is going to respond to that ARP request. Here I'm using the MAC of IP address. It's shorthand. It's easier to line things up, and it's easier than typing out 48-bit numbers. Feel free to substitute almost any 48-bit number. I once said any 48-bit number, and one of my coworkers helpfully pointed out that not all 48-bit numbers are valid MAC addresses. So the Ethernet switch learns where 10.0.0.3 is and what the mapping is in terms of L2 to L3, and responds. So at this point, we've got the MAC address for our destination. So now we can send an IP packet. The L2 and L3 source and destination match up because this is traffic within an L2 domain. And the switch can deliver the packet to the end. This is Ethernet as it's been used for decades. We have to make it work in the cloud. So as always, the guest is going to ARP for its destination. It's going to say who has 10.0.0.3. We're going to trap that ARP packet in our physical server. We're going to send it to the mapping service. And we're going to say we need to know where blue 10.0.0.3 is. The mapping service is going to tell us that blue 10.0.0.3 is down there in the lower right corner at 192.168.1.4. And by the way, here's its MAC address. And so using that, we can send the ARP request back to the guest. So at this point, 10.0.0.2 believes that it is ARPed for its peer. It turns out, and you can actually test this in VPC, we don't ever actually propagate the ARP request to the destination. It turns out that doesn't matter. None of the Ethernet implementations that exist in the world depend on that. And so at this point, 10.0.0.2 has everything it needs to send a packet. So we're going to craft exactly the same packet that we would have sent on a physical network. This instance is not aware that it's running in a VPC. We're going to trap that packet. We're going to wrap it with a VPC header. Then we're going to wrap it with a physical network header. So we're going from 192.168.0.3 to 192.168.1.4. We can send that packet straight to the destination. Now, 192.168.1.4 just gets this packet out of the blue. Like, what on earth is this thing? So it's going to ask the mapping service, is this cool? I just got a packet from 0.3 claiming to be on behalf of blue 10.0.0.2. Should this packet exist? The mapping service is going to say, yep, it's cool. It also happens to include the MAC address for 10.0.0.2. So we can reconstruct the original packet that the customer sent and deliver it to the instance. So this is Ethernet off the operating system DVD. These two guests have not been altered in any way. This is a traditional network as far as the guests are concerned. In order for these two instances to communicate as if they were in a VPC subnet, they have to be able to talk to the mapping service, and they have to be able to exchange IP packets. But that's a solved problem. We already know how to build IP networks that span the globe. These two physical machines could be located literally anywhere, and they could participate in the same VPC subnet. And so that means that the VPC L2 topology is completely decoupled from the physical topology. I don't need large physical L2 domains. I can lay out the L2 in the physical network however I want, however the network engineers deem best for that data center. So let's dig in for a moment on that reverse mapping check on receipt of a packet. I said earlier that we created /0 VPCs in testing. It was a fun way to test the software. It's not a useful thing to ever do in the real world. But literally, this guest can scan the entire IPv4 space. Any 32-bit number they can cram into the destination they can scan for. And when we query the mapping service, we're going to query it in the context of their VPC. They can't physically cram bits into the header to cause a packet to be addressed across VPC boundaries. Now, what if, for whatever reason, the query is awry? They're going to query on behalf of Blue. The mapping service knows there aren't any Blue instances on that lower left physical server. There are no Blue instances on 0.4, so the mapping service is going to deny the mapping, and it's going to call for a human. And we know this works because it goes off when we test. This is an alarm that we test regularly. And so this server here, 192.168.0.4, can't even fetch mappings for which it is not authorized. If by some series of events, we obtain the mapping and we can construct the packet and send it across the physical network, we're going to do the reverse mapping check. The mapping service still knows that 192.168.0.4 shouldn't be hosting any Blue instances. We're going to let the destination server know that the mapping is invalid, that the packet should be dropped, and again, we call a human. And so what this means is that packets cannot and will not flow unless every participant, the source, the destination, and the mapping service, agree where everything is placed in the network. This is a property you don't get in physical networks. Spoofing in the VPC network is not possible. So that's L2. We also need to propagate L3, IP packets. I'm assuming a /24 net mask here. And again, this is IP as it's been working for decades, straight off the operating system DVD. So the Ethernet switch is going to do the exact same flooding dance, learn the MAC address, but in this case, we're ARPing for the gateway. Because we know, based on the net mask, that the eventual destination, 10.0.1.3, isn't in the local subnet. So we need to ARP for the gateway. We ARP for the gateway. We learn a MAC address for it. Now we can send a packet. This packet is different. The destination MAC address is the gateway. It's the MAC of 10.0.0.1. The L3 destination, the destination IP address, is the eventual destination across the router. We send the packet to the router. The router transforms the packet. It replaces the L2 source with its own MAC address in the 10.0.1/24 network, decrements the TTL, puts in the destination MAC address of the eventual destination, and propagates it across the second Ethernet switch. Again, Ethernet off the operating system DVD. So I've swapped out 10.0.0.3 for 10.0.1.3 in the lower right corner there. We have to propagate this exact same packet flow without altering the software that's running on the guests. So again, the exact same thing happens. We ARP for the gateway, send it to the mapping service, get back a mapping. And in this case, the host isn't a physical server in our network. It's tagged as a gateway. This tells the server that packets sent to this destination, this L2 destination, need to be handled specially. So at this point, the guest believes that it's ARP for its gateway. Now, we can craft that exact same packet. This is going to be trapped because the destination L2 MAC address is a gateway. We're going to trap it. We're going to do a secondary query to the mapping service. And this time, we're going to look up the destination IP address, not the destination MAC address, because this packet needs to be routed. We're going to get a mapping. It turns out that we return the MAC address for the host that's on the far side of the router. We don't propagate it back to the guest, but it turns out we actually do propagate it. So now that we've got all the information we need for a mapping, we construct the packet, wrap it with a VPC header, wrap it with the exact same physical network header, and deliver it across the network. We're going to do the same mapping check on receipt. Please validate that this blue 10002 is actually from this physical source. We're going to get an indication that the mapping is kosher. At that point, we can swap MAC addresses and deliver the packet to the destination. So this has exactly the same properties as the L2 flow. Any two physical servers anywhere on Earth can participate in the same VPC as long as they have IP connectivity with each other and they can both talk to the mapping service. So for both L2 and L3, we have placed 0 additional constraints on placement. We can drive the same utilization of our network, of our physical servers, that we could before the addition of VPC. So we've reduced the capacity management problem of VPC to the capacity management problem of EC2. Now, there's a problem here. There's that I trapped a packet. It's one thing to trap ARPs. ARPs aren't actually in the customer data flow. If your ARPs take a little bit longer, no one notices, and they happen infrequently. Trapping customer packets, you're going into debt, you're queuing them. Customers care about their packets, they're precious. And the network, the physical network, they don't get lost. And so we don't want them to get lost here, so that means we need to save them. But then you have to allocate space to save them. And customers use the network in all sorts of interesting and exciting ways. And you don't know how much queue space you need. And so what we actually do is we have a cache of the mapping service on every single one of our physical servers. And they all subscribe to the mapping service. So all of the behavior that I described earlier, it is how the system actually behaves. Everything is organized into topics. Individual servers subscribe to topics. They can't subscribe to topics that they shouldn't have access to. So for example, 192.168.03 is allowed to subscribe to the blue topic and the green topic. But 192.168.04 in the lower left corner, it's only hosting gray instances. It's not allowed to subscribe to the blue topic. If it attempts to subscribe to the blue topic, we deny it and we call a human. And so in reality, we didn't even implement the cache miss path. We have 100% cache hit ratio. 100% of the mappings that a server needs can be satisfied locally out of this cache replica without going off box. And that allows us to provide dead flat network latency. So that's how you talk within the VPC. But the whole point of this product was plugging the VPC into your on-prem data center. And so we've talked about how L2 flows work within a subnet. We've talked about how L3 flows work between subnets. And we've solved the high-velocity routing table updates. We've allowed you to bring your own IP addresses. But you need to be able to send this packet. That's fine. It's a packet. It's going from 10.0.0.7, which is one of your instances. It's going to some IP address in your data center. Our router on our side totally knows how to send that packet. We can wrap it with a VPC header. I don't know what your router is going to do with a VPC header. But then we're going to wrap it with a physical network header. I have no idea what to plug in for that destination IP address. Plus, I mean, if I did, if you gave me an IP address, like, what is your router going to do upon receipt of this Amazon proprietary packet? And so we're going to introduce a new concept here, and that's edges. We've got this mapping service replica running on every host, and it's got all of the mappings that it needs to communicate within the VPC, but there's also CIDR mappings. So in this case, we've got a mapping that says 172.16.0.0/16 has to go to this edge. And this is the implementation. This is the physical implementation of routing tables in the VPC. And so if you look at this packet flow, it looks exactly like the packet flow we had before. We're going to take the packet, we're going to wrap it, we're going to send it across the physical network, the edge is going to do the reverse mapping check, and then what? So in this case, we're talking about a VPN connection. The edge, it's an AWS-owned device. It's a Linux box with a whole bunch of NICs in it running our software. And so it knows how to interpret this VPC packet format. So we send it to the edge. We strip off all of the VPC proprietary stuff, We wrap it with an IPsec header and a physical internet header. And in this case, the source and destination IP addresses are internet routable. That source is actually one of our VPC head ends. And the destination, well, you can look it up yourselves. But if I send this across the internet, it is conceivable that you have a device in your data center that can handle this packet, that can unwrap the IPsec header inside, extract the original packet. And so now we've enabled an instance inside of a VPC to talk to a router in a data center, through a router in a data center, to a host in a data center, using IPsec, which is, I don't know, it's supposed to be standard. It's mostly standard, kind of. We also have AWS Direct Connect. Rather than doing IPsec and crypto over the internet, you can get a line, a physical connection to AWS, 1 gigabit, 10 gigabit. And in that case, we do exactly the same thing. We deliver the traffic to an edge. In this case, it's an AWS Direct Connect edge rather than a VPN edge. We strip off all of the Amazon proprietary stuff. We wrap it in a VLAN tag, and we deliver the packet. These VLANs are pretty short. I said earlier, 12 bits, 4096 is a problem. This is literally the cable from our edge to the Direct Connect router. And so when 4096 isn't enough, well, you've probably saturated the bandwidth on that link anyway, and you get another link. In reality, we've never come anywhere close to the 4096 limit. These VLANs are literally single-digit meters long. And then people like talking to the internet. There's good stuff on the internet. Actually, a lot of us live on the internet. You want to talk to your instances. So we have to do that. And we all know that sending a packet with a 10002 IP address out to the internet, like you're totally allowed to, it completely works. You're just never ever going to hear back from them. So we need to send this out. And it turns out we actually just want to send IP traffic. We don't want it to be wrapped with anything. So we extract the packet. And this is where we do elastic IPs. We swap out the source IP address. So it's source NAT on the way out, it's destination NAT on the way back in. We swap out the IP address so that someone out on the internet that chooses to respond to you has an IP address that's actually routable that'll get back to you. And so this is how we do internet connectivity in VPC with elastic IP addresses. So these are the 3 edge types that we support in VPC. So Tux, the Linux mascot, is a penguin. There's a lot of penguin metaphors running around in the Linux world. We are not immune to this. It turns out that EC2, a good chunk of EC2 got its start in Cape Town, South Africa, which, interestingly enough, if you take a globe and you put it on a drill press and you start in Seattle, you come out in the Indian Ocean just off the east coast of South Africa. This is almost as far as it's possible to get without leaving the planet. Just south of Cape Town is Boulders Beach. And on Boulders Beach, there's the African penguin. They're also known as the jackass penguin. It's very disconcerting. They really do sound like donkeys. But they're also known as the Blackfoot penguin, for obvious reasons. And so when we built a Linux networking appliance, it's Linux, and it's Amazon, and it's EC2, and EC2 got its start in Cape Town, we named it Blackfoot, which is also where the building in Seattle, where a lot of us work, got its name. Recently, I heard that we had dropped prices in AWS for the 51st time. None of these have been VPC price drops. VPC does not participate in the grand Amazon tradition of dropping prices because due to the implementation that we haven't additionally constrained placement, so we haven't driven down utilization. We aren't using expensive routers with weird ASICs in them. So the cost per VPC is 0. Go into the console, go into the APIs, create a bunch of VPCs. It will not affect your bill at all. Subnets are also free. And most importantly, the difference in price between an instance that's connected to a VPC and an instance that isn't is 0. This is the date that we turned off the last physical web server in US retail. And if any of you are familiar with the way retail works in its annual cycle, that's a scary date. That's very close to Black Friday. And so in 2010, we carried 100% of US retail's traffic in VPC. So this is not a science project for us. All of the slides that I went through would have made an interesting conference paper. But it's not I don't have a beautiful LaTeX formatted document, unfortunately. But we do have working software. And this is working software that's carried the US retail load for 5 years now. This is the software that we bet our business on. This is how we operate Amazon today. So this is not a research project. This is a real honest-to-God launched product. And it's been a lot of fun watching it evolve. It's been around for a while, and we've always had the ability to attach instances to it. We've added a whole bunch of other resources to VPC. So now you can have an RDS database. And so you can have clients, you can have end users in your offices, in your data centers that are talking to this RDS database as if it were a seamless part of your network. You can have Redshift clusters, data warehousing clusters running in your VPC, consuming data from data sources on-premise. It's a seamless network that spans both your data center and AWS, and you can mix and match resources, and we keep adding services to VPC. So in EC2, we didn't say much about the network. You had an IP address, you had a public IP address. That was really all we said about the network. Like, you had an IP address, you could send packets to it, and you would get packets back from it. And that was the entire network abstraction. And it was great because it was easy to get started. You'd click and you'd get an instance and you could SSH to it and life was good. But there was nothing more you could do with the network. And so we've added VPN and Direct Connect. And this is the platform on which we do all of our network innovation now. So security group egress filtering was a common customer ask. That's available in VPC. Network ACLs. A lot of traditional networks, you group like things together. As you physically build the data center, this subnet is over here, and all of the web servers are over here, or all of the payment servers are over there. And so it doesn't have to be that way, but in many customers' minds, and this is neither a good thing nor a bad thing, it's how they think, IP addresses that are close together are related to each other. That's fine. Put them on a subnet together, put a network ACL in front of it, you can lay out your network that way. We added routing tables. This allows you to have granular control, completely driven via APIs, over where your traffic flows in your VPC, and this allows you to interpose network appliances inside of your VPC. To say all traffic between this subnet and that subnet is going to flow across this appliance, which we now support multiple ENIs, elastic network interfaces, on an instance, and so you can build a network appliance, and we've got a whole marketplace full of vendors that provide network appliances that work in VPC. And multiple IP addresses per ENI. And so we've got this platform now where we're constantly adding new features, and one of the cool things is that because it's delivered as a service, there's no deployment, there's no upgrade. When we release a new VPC feature, all of our customers can take advantage of it immediately. It's an API call away. And one of the coolest things that we've launched recently is S3 endpoints. So prior to S3 endpoints, if you wanted to talk to S3, you needed to egress to the internet somehow. You could do this down your direct connect or VPN link to your data center and then back, but that's the long way. EC2 lives here, S3 lives here, your data center's over there. You're paying the speed of light twice, you're paying bandwidth twice. In some cases, that's the right thing. You've got some set of security appliances or inspection on-premise, and you want to apply that, that's fine. We support that configuration, but the latency and the performance aren't going to be there. And so you've got to have some way of egressing to the internet, whether it's an internet gateway local to your VPC or down a direct connect private link, and then you need to hit S3. In that case, you must have a public IP address. S3 has to be able to send packets back to you. If you egress with an RFC 1918 IP address, we're not going to be able to talk back to you. So customers didn't like this configuration. They gave us feedback. We listened. And so now you can declare an S3 endpoint. It's an API call, just like everything else. And you say, I wish I had an S3 endpoint attached to this VPC. And then your instances talk to your S3 endpoint without needing to have public IP addresses. And the endpoint takes care of talking to S3. And I'll tell you how in a moment. And so now you've effectively moved S3 into your VPC. You don't need to have any internet exposure whatsoever in your VPC. You can talk to S3 via the fast path. You don't have to haul things back to your home data center. And the way it works is we added a new kind of edge. And so the VPC network itself doesn't need to change at all. VPC doesn't know if it's delivering to a VPN edge or a direct connect edge or an S3 endpoint edge. So this allowed us to decouple our engineering. And so all we had to do is say, if you're going to S3 US East 1, if you're going to this named prefix worth of IP addresses, send it to this 192.168.4.4 edge. And so We're going to send something to S3. It's probably going to be HTTP, at least if you want a response back. We're going to do exactly the same wrapping that we've talked about before. We're going to send it to the destination edge. It's going to do exactly the same reverse mapping check. And now we've got this thing. We're going to send it to the edge. And what we're going to do is we're going to unwrap your packet, and we're going to rewrap it with a wrapper that S3 understands. We taught S3 how to understand endpoints. And so when this packet arrives at S3, we don't NAT. The source IP address there is still 10.0.0.2. And the VPC endpoint ID is encoded in that packet header. So when S3 gets this packet, it knows which VPC and which VPC endpoint were used to reach your bucket. And that leads to some interesting features. You can apply policy to the endpoint itself. And in this case, I've got a resource allow statement in this policy. And the only thing that's accessible from this VPC is my secure bucket. Any attempts to get to any other bucket from that VPC going to be met with a permission denied. You'll actually get a permission denied error from S3 saying, I'm sorry, that's disallowed by policy. And so now you can control which buckets your VPC can get to. You can also apply policy to your bucket. You've always been able to do this. But now, we've added the ability to specify an endpoint ID. And so this is a deny clause that says, if the endpoint ID isn't this specific endpoint, deny the request. You now have a bucket that is only accessible from within your VPC. I could create this configuration. I could give you my AWS credentials, and you still wouldn't be able to access my bucket. And so now, from VPC to S3 all the way through, using the same standard AWS policy and IAM controls, you have complete control over your traffic end to end. So in product design, we often face a tension. You've got products that are simple, products that are complex. And the products that are simple tend to be limited. And the rich, complex products tend to be more flexible, but they tend to be harder to use. And this isn't a value spectrum. I own both a multimeter and an oscilloscope. They're both good tools. I use them for different jobs. I wouldn't want to get rid of one for the other. But if you're trying to figure out if a battery is good, getting your oscilloscope out is really silly. If you're trying to debug a clock circuit, the multitester is just going to stare at you blankly. And what we had was two separate experiences. We had EC2 and we had VPC. And customers would use EC2, again, through no bad thinking. There's the getting started guide. It has like 3 steps. You want an instance, you need to create a key pair, you need to pick an AMI, you need to launch the instance. You're in. Oh, wait, you wanted a VPN tunnel? We're sorry, you need to be in a VPC. It's not a good customer message. So a few years ago, actually in March of 2013, we launched default VPC. And this is the experience that all new AWS accounts get. So you can go through the Getting Started guide. The Getting Started guide from 2010, back before EC2 had all of these features, back before VPC existed. You can launch instances and you can terminate instances. It's completely code compatible with EC2. And so the code that was written by us, and more importantly, the code that was written by our customers, by the ecosystem of people that have been using EC2 for years, continues to work. And if you ever want any of the rich advanced features of VPC, you break the glass, and it turns out there was a VPC behind you all the time. And now you can bring up VPN tunnels using exactly the same sequence of API calls you would have made if you'd explicitly declared that VPC. So we take care of all of that initial muck for you. We don't impose the complexity on customers. But then when they want it, it's there for them. And so as a result, we've now got a single product that spans a fairly broad swath of this spectrum. And customers can incrementally tackle this complexity. They can adopt these features as they're useful to them, but they don't need to deal with them until they're useful. Thank you for sticking around. Hopefully you're not leaving disappointed.